Welcome to the 8-bit theory. In today's video we'll bring some motion to the screen, and we're doing this by using the Commodore 128's VDC chip. So far we displayed CGA low-res in 160 by 100 and EGA medium resolution in 320 by 200, both in 16 colors. But we restricted ourselves to static images only. This is going to change, and for that we'll use features of the VDC chip we didn't use before. The topics I want to cover today are transitions, hardware scrolling, and animations. If you hear me talking about things you haven't heard before or you think should really be explained more in depth, please make sure to also check my previous videos on CGA and EGA graphics. I explained a lot of the concepts there. Very likely you will find the answers there. In the CGA low-res video we rendered this image. Now, if that was part of a slideshow, we wouldn't want to just replace image by image. We'd want to have some transitioning effect. A simple one is blending over line by line. For that, we'll load two images into VRAM. As in all the previous videos, we'll need a C128 with 64 kilobytes of VRAM. The 16,000 bytes for pixels will set each color block to background color in the left half and foreground color in the right half. The 8000 bytes of attribute RAM will actually contain the color information for these. You'll find the exact details about that in the video about CGA low-res. The first image is directly loaded into the visible area. For transitioning, we'll just copy line by line from the invisible part of VRAM to the visible part. And because screen RAM is identical between both CGA low-res images, we'll only need to do this for attribute RAM. I'll be using VDC-Basic once again for showing how to code this. That's a basic extension that makes working with the VDC chip really easy by introducing new basic commands. In previous videos we already used the commands RGW and RGO, which write values or OR values to the VDC's registers. And we also used VMW, which writes a single byte to VRAM. And also VMF, which fills a specific part of VRAM with one value. VMF is a pretty nice command, and what's really special about it is that it's not just VDC-Basic taking over the looping and writing for filling VRAM. Actually, the VDC chip itself has block fill capabilities. That means you define the memory area, the value and the number of bytes to be filled, and the VDC chip will execute that independently. That really means the main CPU is free for other work while this happens. Block fill can fill a maximum of 255 bytes, but VDC-Basic allows you to provide any number. Now, for copying one image over the other, we could just write the according line from CPU RAM to VRAM, or we can use the VMC command. VMC is for video memory copy, and it copies a specified amount of bytes inside VRAM. And just like VMF, this leverages another great capability of the VDC chip, block copy. By specifying source address, destination address and the number of bytes, the VDC chip will do the copying independently. Just like block fill, block copy handles a maximum of 255 bytes, and VDC-Basic will take care of higher numbers again. Let's move to the concept for line-by-line transition. First, we need to find a way to get 100 random numbers because our image has 100 lines. And we want to make sure that any line is only picked once. The solution I came up with is to create a list with 100 numbers. A random number between 1 and the number of entries is generated. That number does not provide the line number itself, only the index to an entry in that list. The entry contains the actual line number. We pick that, then we remove that entry from the list. The next random number will be between 1 and 99, and so on. For every random number, we block copy the line from the source area to the visible area. And this is the code. After loading and activating VDC-Basic, we define the memory address for the required attribute RAM areas. We need 3 of them. One is for the current display, and this will be modified as we want to modify the screen. The other ones contain the data of the two images, and we will only read from them. Similar to previous episodes, we're setting up the VDC for 2 scanlines per color block, bitmap mode, 64K of VRAM, and we reduce the number of memory refreshes. Then we fill screen RAM with the value 15, which sets up each color block for background color on the left-hand side and foreground color on the right-hand side. And we fill all attribute RAM areas with zeros. Finally, we set the start address of screen RAM to 0 and attribute RAM to the start of the first image as defined earlier. Right after that, we create the list of 100 entries in Y string. This is just a string containing the byte values between 1 and 100. This is done by using CHR string. I really like to use strings when I need lists of byte values of variable size. Arrays would be much too cumbersome to use here. Then we load the first image, and we copy that to VRAM right away. Destination is the visible screen. Here we use RTV, that's the VDC-Basic command for RAM to VRAM. First parameter is source address in main memory, second is target address in VRAM, third is amount of bytes to be copied. I also added S as a timer variable. That way we can track the difference between how long copying from main memory to VRAM takes and how long copying inside VRAM takes in comparison to that. So this is our little benchmark for this episode. D and A are offset variables. D represents the image data in main memory. A is the destination address in VRAM. And for loading the second image, we set them to different values, and we can reuse the loading procedure thanks to that. Now we have both images in VRAM. The first image basically resides in the VRAM area that's rendered to the screen. That means it will be overwritten once we transition in the other image. So we'll still need to store it somewhere else for being able to transition back and forth as often as we want. And here's the other measuring point for our benchmark. S remembers the current time just like before, and after the VMC command we calculate the duration and print it. I explained VMC earlier, that's short for video memory copy, and it issues a block copy command to the VDC chip that solely operates inside VRAM. Then the random number generator is initialized. In Commodore Basic, this is kind of rocket science to get it done right. I'm using -TI for that. You'll find all the different ways to do this on the internet. Now we finally come to transitioning. We're looping through 100 iterations for the rows of the image. First, we draw the random number, and we pick the row number from that index. That number we convert into a VRAM row offset by multiplying this by 80. That's because each row consists of 80 bytes, each one representing 8 pixels, which equals the horizontal resolution of 640. So each line of our image starts at an offset address at a multiple of 80. Then we remove the current entry from the list. And while this might look cumbersome, it is actually much easier than manipulating an array. And we finally call VMC. CS is the source address, CD the destination address, and we copy 80 bytes for a full line. As mentioned earlier, we only deal with attribute RAM here. We could just as easily add another VMC command to copy screen RAM if that was necessary. Now let's run this. Copying from main memory to VRAM took 26 GFs. That's just below half a second for 8000 bytes. And copying inside VRAM of the same 8000 bytes just takes 1 GF. That's effective immediately. I think this clearly shows the potential of the VDC chip. And now to the transition. Unfortunately, there's not a lot of CGA low-res images around, but I still managed to find a real good one. The artist of this landscape is Emiliano D'Alessandri. On Instagram he goes by Clockmaster77. I'll put a link to his social media presence into the description. Thanks a lot, Emiliano, for letting me use this image. And thanks to the first image also being stored in VRAM separately, we can always transition back. This image is already known from the CGA low-res video. It was created by Michael Martin, and I'll also put a link to his blog into the description. How else can we transition between images? By sliding out and sliding in. And for that I'll introduce you to hardware scrolling. Now how does that work? Scrolling the vertical way is the simpler case. Let's start with that. Due to the large amount of dedicated video memory available to the VDC chip, nobody keeps you from writing more data to VRAM than what's visible on screen. In addition to that, you can define from what address the VDC chip should start reading data for being displayed. When you then move the start address of screen and attribute RAM for the number of bytes of one line, the display scrolls for exactly one line. Actually, I'll use monochrome mode to demo this, as we didn't use that mode yet. I took the title screen from the Bard's Tales Macintosh version, which is black and white, and the native resolution of the first Macintosh is 512 by 342. That's an easy fit horizontally, but not vertically. So let's just load this image and make it scroll up and down. The code I'm showing here is an older piece, not written just for this video, but part of my early research on the VDC chip. After setting up VDC-Basic, we initialize some variables. Initial row width IR is 64, and 64 by 8 is 512, which is the horizontal resolution of the image. You'll see why we need this in a variable. And R is our working variable for that. Register setup is a bit simpler for monochrome. We disable attribute RAM altogether, so all memory is available for pixels in just two colors. And we don't need to do any color block setup here. Also, we set the number of visible characters to 64, the width of the image as mentioned in the variable block. So the screen is now really just 512 pixels wide. Then we get the image onto the screen. As I said, this code is old. Rendering is done line by line, upside down, and all these numbers are hard-coded, but I think in the meantime you know what has to be done here. So yeah, this just gets the image onto the screen. Print CHR string 7 is actually a non-printable character, but it triggers the SID chip to issue a beep. We do this because image rendering takes longer than what we can see on the screen, so when the bell rings we know that the program is waiting for input. And then we enter a loop, and querying the keyboard for input is the first thing we do. On cursor up or down, we add or subtract 64 bytes to the VRAM start address, one full row of the image. I also added cursor left and right to modify the start address for just a single byte instead of a full row. I'll explain what that does when we run the program. If a cursor key is pressed, we also set a flag for updating the start address. The VDC-Basic command disp is doing that for us, so we don't have to calculate low and high bytes. Then we check the space key to toggle the speed between 1 and 2 MHz, and we allow plus and minus keys to increase the scrolling offset. In that case, we also print the offset address to the VIC screen, so we know what the current offset is. And while we are at it, the VDC chip has a register for reverse mode. That's bit 6 of register 24, so we will just listen to the R key to toggle that. As you probably know, setting bits is done through an OR operation with 2 by the power of the bit to be set. Clearing bits is done by an AND operation of 255 minus 2 by the power of the bit to clear. Okay, let's run this. With the screen 512 pixels wide, it doesn't span across the whole display, so the image doesn't adjust automatically with changing resolutions. You need to use the knobs on the monitor to stretch the image. We can see the image building up line by line. And here's the signal. Now we can scroll up and down, and you see that this is going pretty smoothly. It is so amazing that this is 99% Commodore Basic with just a small basic extension that allows you to do things like these. Now we toggle fast mode. You can see that we're in fast mode when the VDC-II display is disabled. Changing the speed doesn't make a real difference, it seems. And the reason is very likely that the disp command waits for the next vsync to happen before it actually applies the new start address. So 2 MHz doesn't make a difference here. Let's increase the scrolling offset by pressing plus, and this clearly does make a difference. Now let's try the reverse mode. Nice! The 8-bit guy showed Planet X3 on a monochrome LCD display, and readability of the screen was much better in reverse mode. I guess no 128 will use one of these displays ever, as there is no luggable 128. But if so, here's the easy way to provide reverse mode. And now for left and right. It looks as if we are scrolling horizontally. We are, but not as you'd expect. Actually, the image shifts up or down by 1 pixel, so the longer we scroll, the more it shifts. And that's the perfect transition to horizontal scrolling. The first pixel of a scan line is usually the next one after the last pixel on the previous line. What we see here is just wrapping over the end of the line to the next pixel. Now, say we wanted to scroll horizontally between these two images. For correct horizontal scrolling, we have to add one additional piece, address increment per row, meaning when the end of a scan line is reached, how much should the address be incremented before reading the byte for the first pixel of the next line? In our case, each image is 80 bytes wide. After the first line, we'll need to skip the 80 bytes of the second image's first line. So we need to set register 27 to 80. And as one register can hold 1 byte, the maximum number of bytes to skip is 255. If we set address increment per row to 80, we basically render each other line. In the lines in between, we can place another image which is actually displayed next to it. And of course, we can also load one big image with twice the horizontal pixels instead and make it a scrolling screen. It's important to mention that for full resolution you can only really scroll 2 screens wide, as each screen will take 24K of memory. For CGA low-res you can do 6 screens, as you'd only have to scroll attribute RAM. And for monochrome you can scroll between 4 screens. And of course you can scroll in both directions, so you should be able to scroll a monochrome image that's 2 by 2 screens in size, for example. That's 1280 by 400 pixels. And now let's put this into practice. What I did next was to find 2 images that would make for great horizontal scrolling candidates. And I decided for Space Quest 1's starting point, the Arcada. Space Quest 1 doesn't scroll between screens, but that doesn't mean we can scroll them. Games based on Sierra's AGI engine have a screen resolution of 320 by 200, but the game scenes themselves actually only use 160 horizontal pixels. So each pixel is stretched horizontally. I merged 2 screenshots into one large image and fixed the color constraint violations in Promotion NG. Check the video on EGA graphics to see more details on how this works. The merged bitmap is 320 by 168 pixels, but when rendering it would be multiplexed to 1280 by 168 to fill 2 VDC screens. You'll find the exact code for this conversion on GitHub. As the changes to all the conversions we did so far are minimal, we'll just look at the viewer program here. And the only change worth mentioning there is in line 210, where we set address increment per row to 80, resulting in a virtual line size of 160 bytes. Then we print keyboard commands on the screen and we enter a loop to check for keyboard input, process that, and bring the changes to the screen. Possible options are scrolling left or right and toggle the address increment between 0 and 80. At the end of each iteration we update starting locations for attribute RAM and screen RAM. This is what actually makes the image scroll. And this is how it looks. It looks exactly what we thought it would look like, right? And also, scrolling works flawlessly. So we scroll back and forth. And then we also toggle between the virtual line sizes of 80 and 160. It looks beautiful. But before you celebrate a fully scrolling version of Space Quest on the C128, we need to talk about emulating the VDC chip. While this looks fine in Wise, it doesn't in C64K. C64K is another emulator, and not just any other emulator, but the one that emulates the VDC chip more accurate than any other. That means, unfortunately, this is also how the screen looks on the real Commodore when setting address increment per row to 80 in bitmap mode. But it's very important for me to also mention that address increment per row works perfectly fine in text mode. So any Petscii art text mode screen you might be doing they are perfectly scrollable and working without issue. And as I'll talk about in a future video, text mode on the VDC is far more powerful than on the C64, so this is a lot better than it sounds right now. Okay, now why is the image broken here? My theory is that it has to do with how and when register settings become effective. Some become effective immediately and some only when a new frame is rendered. I won't go into any more detail here, please check the description for 2 links that might provide a proper answer to this. The block shown here originates in a project on Hackaday to create the VDC-II chip with backwards compatibility. The author did a lot of digging into the internals and he brings up a lot of interesting points. So much for horizontal scrolling, at least for now. I also intended to cover animations today, but as this video is getting really long already, I'll just leave this here as a teaser for one of the next episodes, which will be exactly about that, animations. I think the most interesting technical pieces about today's episodes are the block copy and block fill commands. You can trigger these and the VDC chip does the heavy lifting by itself without consuming any cycles on the main CPU. Vertical scrolling is really easy and 64K of VRAM allows for enough space to really leverage on that. Horizontal scrolling seems to be a bit of a troublemaker, however, and I think there will be another episode on hardware scrolling as soon as I can explain the reason for this behavior. So if you have a solution to this, please reach out and let me know. In addition to that, the VDC chip also has smooth scrolling registers that would allow for single pixel scrolling instead of byte-wise scrolling, but I'm afraid that will be just as troublesome. Also, hardware scrolling really only works across the full screen, and even if it works, it's probably just a good candidate for intros and full screen artwork, but not so much in games where you have borders and text overlays, etc. So, for scrolling a map like in Ultima or Petscii Robots or Planet X3, we'll need to look into tile-based rendering anyways. If you found this video interesting, please make sure to give it a thumbs up. I already mentioned that I'll talk about animations in an upcoming episode. Besides that, I'll also talk a bit more about games and genres that would make for good candidates for a VDC port. And besides that, I have even more on the list, like tile-based rendering, software sprites, and the very powerful text mode that I already mentioned several times. So please make sure to subscribe to the 8-Bit Theory to not miss any of that. Thanks for watching, see you next time.